Hello and welcome back. We're continuing our discussion about trees by finishing off our conversation here with the deletion of 2-3 trees. Some of these notes still have some writing on them from previous run-throughs of this, but I'll just delete that as I go. So the deletes are complicated, and so we mostly go through them in theory with no expectation for you to be able to implement it at this time. But deletes start the same way that they start in a binary search tree, which is just searching for the value to be deleted. And there's a couple of different cases that we need to consider when it comes to deletion. The first one is the deletion of an internal node. So if the value that we wish to delete is found in an internal node, so like one of these ones, we're going to swap it with its immediate successor, which, as we know, must be a leaf node. This way, we're always going to be starting our delete operation at a leaf node. So let's give this a shot. The easiest case is our consideration for deleting a leaf node. More specifically, a leaf node that contains another piece of data. So it would be just like any other scenario. For example, if we're looking at this right here, we wanted to delete the value 18, we'd go find its successor 19. These two would swap and we'd be deleting this same position, right? So that finding of the successor and doing that swap sort of doesn't change what we would do. The question is just what are the different configurations of leaf nodes that could affect how our delete is going to work. So here we're going to delete 19. It's simple enough. If there are more pieces of data in here and we just need to delete one of them, we can just make sure that we move everything over. And that's it. That's all there is to it. We would just delete it. It would be gone. We would just have 21. And our tree is still balanced. The leaf node is still valid and everything is good. Now let's look at a slightly trickier case. Here we see a case where we're going to go ahead and try to delete 21. Now in deleting 21, what we clearly see happen is that we no longer end up with a balanced tree. We end up leaving a gap, and we can't have a gap in a balanced search tree. However, when we look at our sibling, this is us like taking a look at our sibling right over there, we see that our sibling has 2 pieces of data in it. And so since our sibling has 2 pieces of data, what we're going to do is we're going to do a little bit of a swap and move, perhaps. Maybe that's the easiest way to say it. What we end up doing is kind of what we see in our next lecture with AVL trees. We end up with almost like a rotate, where we punch this max value up and we punch this down. So we get almost a rotate that's happening here. It's not quite a rotate because it's really just like the rotation of the values internal. It's not actually the rotation of like the nodes themselves. We swap the max value from the sibling up to become a parent, and then we take the parent value and we use it to overwrite the previous leaf, thus leaving us in a position where we are once again a balanced tree. So when we have a node that has a sibling with 2 values in it, it's a relatively easy rebalance for us. Okay, let's look at another example here. We'll see something very similar here. If we go to delete 1, we notice that, the node that has 1 in it only has the 1 value, but thankfully one of its siblings does have 2 values. So we delete our 1 just as we'd anticipate, and we can do our little shift here as well, where we can push that 4 up, push that 2 down, and end up in, whoops, that same position that we were in previously. We just redistribute those parents and siblings, keeping our tree nice and balanced. We can even just do one more on the other side very quickly here. If we go to delete 25, thankfully our sibling has 2 children. So what ends up happening is 26 comes down here, and 27 would move up here, and really 30 would move over into the first spot. as we know. There we go. That rotate gets completed, and we once again leave our tree balanced. So slightly trickier because of that little swapping rotation of values, but it's not terrible. All right, let's look at another case here, and let's just get rid of our old notes. The trickiest case would be us deleting this value 5. Because what we see is that the node containing 5 only has one value, and so do all of its siblings. There's nothing left for us to do here. So removing this will potentially be quite problematic for us. So what is it that we can do? Let's take a look here. We go ahead and we delete the 5, and then we're going to merge our empty sibling with another node. So what we actually did was we merged them together, almost like this. That didn't turn out to be quite the way I wanted it to be. That's mostly fine. There we go. It's almost like we did that, right? It's empty, so we just kind of merged it together like that. We merged it with an adjacent sibling. So now there's a space right here as well. And because we're leaving that empty space there, we can pull a value down to keep our tree looking balanced. Now, I'll go ahead and show that. See, that's what we're going to do. Before I do that, though, we're just going to look at this and recognize that we can't leave it in this state, because if a parent has 2 values, there has to be 3 children. If a parent only has 1 value, then we can have 2 children. So since there are 2 values up here, we recognize that we're going to have to move one of these down. Otherwise, we'd have to find a way to create another child. But there is no other child. We only have 4 pieces of data here. And so there's really only one configuration that works in, which is having 1 piece of data up here, 2 over here, and 1 here, or 1 over here, 2 over here, and 1 here. So we can really sort of like take each of those spaces and think about those different cases in terms of the amount of different pieces of data that we have, right? So we have the case of, I'll just do it with like A, B, C, D, E, F. Because in 3 nodes, the most we could have is 6 pieces of data, right? We could also do A, B, C. And this will all be like a delete B scenario. So we could also do this as a potential scenario. We could have, those 2 are handled the same, really. We could have A, C, B. I'm sort of in my own worlds here, actually. We could have up to A, B, C, D, E, F, G, H. I should have actually drawn it out. G, H. Right, so there's the scenario where if we're gonna, let's get rid of this and try this again and draw it properly so that I don't further confuse myself. Imagine for a second that we have 2 different possibilities for root nodes. We have a root node where there's just a single value, or we have a root node where there's 2 values. In the scenario of just a single value, we have a few different possibilities. We have the possibility of that, and that, where what we're looking at is a B, a CD, a BC, a D, or a BC, a DE, or a B, and a C. So those are all the different scenarios when we only have 1 parent, 1 node there. And then we have similar scenarios here. Let's just draw this out. It's not going to be quite as nicely drawn, but it'll be fine. So there's a scenario where we have C, D, and E, C, D, E, F, G. We could have 2 children, E and F, that have only 1. And we could also have all the children having 2 GH. So this is 2 data per child. This is 1 data, 2 children, and 2 data, 1 child. This is 1 data, 1 child, 2 data, 2 child, and this is 1 data per child. We can regroup these as this is also 1 data per child. This one here matches this scenario here. And then these two line up one way or another, basically, with the middle two. So those are really the only different types of configurations that we could possibly find ourselves landing in. This scenario, as we said, was our easiest scenario. This scenario had us just delete child value and be done. So that was nice and easy. That was this one right here. The next case that we considered was if we delete a single value. So this one was deleting when there's 2 values in place and 2 values in place. This one is deleting the single values, but at least 1 child has a pair. And so what we did in those scenarios was, we how can I write this nicely? Pushed parent to delete spot and promoted the joint child to the parent spot. Right, so if we delete D, we ended up pushing A down, pushing C up. If we have to delete D from over here, let's say, we ended up pushing B down and pushing E up. So yes, there's some different scenarios within like the range of these and how they might be affected, right? Here, when we deleted D, A came down. Here we have to delete B for A to come down to this side instead. So there are some configurations within there that we'd have to consider, but they all kind of get handled in that same manner. There we go. And the last, that's also going to be, I guess I should copy this and put it there as well. And then the last one we had to consider was this trickiest scenario right here, where we didn't have a sibling that we could easily steal, which changed things. And that's the one that we are, hold on. That's the one that we are not yet having considered. We've considered our trickiest case being one where we had 3 children and deleting one of them, but we had no helpers, right? So we haven't actually considered the situation where, I'd like to have both of these open just so that we can see what I'm talking about. We actually haven't considered this situation at all. We've only considered this one. This is the one that we last looked at, our trickiest case. So let's just, I don't know what I just did there. Let's just pull this out of here for just a moment in time and separate it from this, because this one we saw, if we delete one, what do we actually need to do? We're just going to delete one and pull a child down. We're just going to do that merge, pull the child down. So merge empty with sibling and pull parent down to new empty spot. All right, so that takes care of all of those cases. This is the only case that we didn't actually talk about. Now, if we just look at it from this perspective, it's not terrible, because all you would really do is if this got deleted, if this was our whole tree and this got deleted, we would just become a single node of A and B. This is clearly the most complicated case. We're not going to look at it right now, but we can see how it might be different. And we can also see how we could handle all of these other cases. So we'll leave it at that for right now with respect to all those different cases. Okay. So we have now walked through that trickiest case of when we deleted 5. We did our merge, we pulled our parent down. Now let's go ahead and look at what we do in this final scenario here. To walk through before we actually write it out in that, where was it? Before we actually write it out over here in this scenario, let's actually just walk through what it's going to look like over here for a minute. Okay, so let's imagine that we did want to handle that situation that I just mentioned, which was us trying to delete this value here. And we are in a scenario of all 3 of these only having a single piece of data in them. So what are we going to do? Let's take a look here. We delete our 18 just as we'd like to do. And we're going to do our merge and pull down just as we'd want. So here we are. We're merging that blank space. We've merged it in here. The next thing we would do is pull down our parent just as we'd expect. And that's totally fine. We've created a valid node. The problem is we've left something invalid right here. We've left an invalid space. So what do we do now that we've left this invalid space? We have to recursively apply our delete procedure again. So now we can look at this one with respect to its 2 siblings. We see that its 2 siblings also are in the single data case. So what we'll end up doing is we'll end up merging these 2 together and pulling down our sibling again, or our parents, pardon me. So we end up with the merge, pulling them together. 11 comes down here. This will all disappear. And this will go right over here. There we go. So we end up with more of like a recursive situation when we have that one scenario, and this could continue to occur. And we'll just show what that ends up looking like. This is the next step. We've merged them together, pull our parent down, and now we have reached a state that's reasonable. Right? The process stops when there's no remaining nodes. So we can see that this one is probably the trickiest one. We can hopefully convince ourselves that each of these cases work. Let's just write up some terminology here for this last case that we just separated out, because this actually works exactly the same as this one. Copy. Oh. Paste this right there. This will work exactly the same, but we probably will need to recurse if invalid. That's a very important step. So to finish this off, I'm just going to erase this right here. And I'm going to just draw what happens when we do these different types of deletions on the other side. So once we did this deletion, let's say we delete D. Let's just write that. Delete D. I'm just picking one. We'll end up with B up here. We end up with C comma A over here. We end up with E over here. If in these 2 scenarios, this one we're going to delete B. This one we're going to end up deleting. I wish I'd kept the numbers the same, or the characters the same, but whatever. If we delete B or C, we're going to end up with, let me just move this over so I can keep them somewhat near their counterparts. C comes up, A goes down, D ends up there. When we delete C from this one, we'll do the same thing. We're going to end up having to do a swap and rotate sort of thing here, where we're going to end up with D and B up here. A came down, E got left here in the middle, and F and G were over there. Okay, let's just move these over so we can continue the same way. Here, if we delete, oops, this is exactly the same scenario as this one, just on the opposite side, right? So if we delete D, we would do the exact same thing where C would end up here, B would end up here, A would end up here. Those are identical. Over here, it's only slightly different. If we delete C or D, it doesn't really matter. If we delete C, we have some extra like movements that have to happen, because what will happen is this will, oh, whoops, sorry. This will have to go up to here. This will have to come down to there. This will have to go up to there. This will have to come down to there. So what we actually end up with is A ends up over there. B ends up over there. D ends up here. That's going to have to be bigger. D and E end up here. And F ends up here. So we had to do like a full redistribute because we merged with our sibling, and then we were still left in a state that was not going to work appropriately, right? So depending on which one we deleted, we did end up in kind of different wonkier states. Let's continue here. These two were really easy. If we delete B, whoops, delete B, everything stays the same. We just delete the value. Same with this one. If we delete G, doesn't matter. They're all the same. C, D, E, F, H. And then our final scenario was this one right here, where we would delete, let's say, B. And when we delete B, we would do a connection and merge. This would end up basically being blank. It would have pulled the C, the A down. And we would have to recurse. And the base case is, of course, this such a scenario where there's no parent above us. So we need to redefine our root. And we could redefine our root as follows. Okay, those are all the different scenarios for the delete. As it says, you won't be asked to reproduce this in code. Some of these kind of simple cases, like the ones that don't involve lots of recursing back up, are pretty easy to do. So those may pop up again, but you know, you'll get some notice. None of these are terribly difficult on paper, at least. Okay, that's everything for our 2-3 tree delete. Our next video that we're gonna create and walk through is gonna be one more type of tree, which is our AVL tree, named after two individuals who created that type of data structure algorithm set. And we will walk through AVL trees next. Thanks everyone, and have a great rest of your day.